So now let's do the second example. The second example is a voltage divider by circuit. So, and then this circuit, there is no capacitor, so no need to remove it. So the next step is, because this is a voltage divider, you need to transform the circuit using the Thevenin theorem. So when you do transformation, you calculate the VTH. This VTH is voltage around here. So this is voltage divider, 18 mega plus 22 mega times 40. So this is the equal to 9 volt. So, and then you need to calculate the RTH. RTH is 18 mega parallel with 22 mega. Okay. For now, I will not do the calculation, because actually the RTH in the value of RTH is not important when you do the KVL, because RTH will not appear in the KVL. Okay. So when you do the transformation, your circuit will looks like this. This is 9 volt, and this is your RTH, and then it is this is 0.82k kilo ohm. This is 40 volt. This is 3 kilo ohm. Okay, this is your transform circuit. Okay, so next is the next step is transfer equation. Transfer equation is ID equal to K VGS minus VGSTH square. So VGSTH is 5 volt. However, K is not given, but ID on and VGS on is given. So you can calculate the K is equal to ID on 3 milli over VGS on is 10 minus VGSTH is 5 square. So this will give you the value of 0.12 milli. The unit is ampere per voltage square. So now you get the transfer equation is ID equal to 0.12 milli. Then this is VGS minus 5 square. So this is your first transfer equation. And then the second, next step is you need to do KVL at the input loop. So this is your KVL. The KVL is minus 9 plus. Here at the RTH, the current is IG. IG is 0. But anyway, I will write it down. IG RTH. And then plus VGS. Okay. Between the terminal, there will voltage drop VGS. And then plus this voltage drop at 0.82. The current is ID. So this is ID 0.82K equal to 0. So this is 0. So lastly you get minus 9 plus VGS plus ID 0.82K equal to 0. Okay, so to do the to get the solution, you need to you have two ways. The first way is by graphical, and the second way is by using the mathematical. Okay, so if you want to do the graphical, you need to have the number of point. So for example, the KVL loop, you need to have the number of point. So this is VGS, this is ID. When VGS is 0, the ID is equal to 10.98. When ID is 0, VGS is 9. So because this KVL loop is linear, this is a linear equation, two point is sufficient. Okay, so next for the transfer equation, you need to have multiple point. Okay, so this is your VGS, and this is your ID. Okay, so the threshold voltage is 5 volt, so the point should be starting above the 5 volt. So we put is 6. So and then the maximum point, since the at the KVL input loop, the maximum voltage the voltage value is 9. So we restrict the VGS point until 9. So we put here, this is 6. Let's say I put it 7, 6, 7. Let's say this is 8, and then this is 9. So you can ignore this one. So when the voltage is 6, you get the value of 0.12 milli. When it is 7, this is 7. 7 minus 5 is 2, 4. This is 0.48. Okay. When the voltage is 8, 8 minus 5 is 3. So 9 times 0.13. So 9 times 0.13 is 1.08. So this is 1.08 milli. And when the voltage is 9, this is 1.92. Okay. So you get this point, and then you can do your graphical solution. So let's say for the graphical solution, okay, for this for demonstration, I will use the Excel so that we can have the graph. Let's say this is your VG, VGS, and then this is your ID transfer, and then this is your IDS KVL. Okay, so the VGS start from let's say I put it 5, 6, 7, 8, 9. So IDS transfer is the K is 0.12. This is 0.12 times milli. This is milli, and then times VGS minus 5, and then this is square. Okay, so for the KVL, we have calculated just now. We have calculated that VGS is 0. This is 9. Sorry, when VGS is 0, ID is 10.98. When VGS is 0, so you need to put VGS is 0, ID is 10.98 milli. Okay, and then when the sorry, it's not should be here, is 0.98 milli, and then when the ID is 0, VGS is 9. So VGS is 9, ID is 0. So you can plot this graph. Okay, so this is the graph. The blue line here is the transfer characteristic, and this is from your KVL. Okay, the intersection point will be around, this is, let's say I put 8 point, this is a rough reading. This is around 8 point, let's say I put it 8.1 volt. So the VGSQ is 8.1 volt. Okay, how about the IDQ? IDQ is around the middle here. So this is the IDQ is around 1 milliampere. So 1 milliampere. So this is the solution using the graphical method. So and then next, what if we do the mathematical solution? Okay, first write down these two required equation. The first equation is the transfer equation. This is the first equation. And then the second equation is from your KVL. From your KVL, you get this is minus 9 plus VGS plus ID 0.82K. This is equal to 0. First equation, this is second equation. The first procedure, you want to have the equation with as a function of VGS only. So from the equation number 2, you define the ID. ID is 9 minus VGS over 0.82K. This is your equation 2A. So 2A insert to the number 1, equation number 1. So you get equal to so this is okay. So you do the calculation, you will get this quadratic equation. Okay. So when you do, you have this equation, the solution will have two solutions. The first solution is 8.07 volt. And then the second solution is minus 8.23 volt. Okay, so which solution will be the valid solution? You know the threshold voltage is 5, the valid solution must be higher than 5. So the valid solution is 8.07 volt. So this is VGSQ. So when you get the VGSQ, IDQ can be calculated from this 2A equation. So this is 9 minus 8.07 over 0.82K. So this is 1.13 milliampere. So this is the solution. So if you compare the graphical, we estimate the VGSQ as the 8.1 volt and then IDQ is 1 milliampere. So it's very close.